Assalamualaikum. Today I would like to present our case study for integrated design project, ECC 584. So the topic that we choose and the place that we choose is Venice, ground subsidence and urban infrastructure risk analysis. So let me introduce myself first. My name is Muhammad Hafizin Afif, and those are my group mate, Aiman, Amirul and Danish.
First is problem identification. Let me explain this in a simpler way. Venice is sinking due to three main factors. The first factor is natural settlement. This process happens slowly over time as the soil gradually compresses under its own weight. It is normal and occurs naturally in many coastal cities. The second factor is tectonic movement, which refers to the slow movement of the earth's crust. This also contributes slightly to the sinking of Venice. However, the biggest contributor was human activity. Between 1930 and 1970, major industrial factories in Porto Marghera extracted huge amount of groundwater from beneath the lagoon area. Continuous pumping removed water from the clay layers underground, causing the soil to compact, similar to how a sponge shrinks when squeezed. As a result, the ground beneath Venice subsided rapidly, with the city sinking almost 12 centimeters within only 4 decades. This situation shows how industrial development without sustainable environmental management can create serious long-term consequences. Although groundwater pumping was later reduced, the effects of that period are still impacting Venice today. Next is the damages. So, what are the impacts of ground subsidence in Venice? There are three major effects. First is structural safety. Venice is supported by millions of ancient timber piles driven deep into soft soil centuries ago. These wooden piles remain durable because they stay fully submerged underwater in low oxygen conditions, which prevented decay. However, as the city continues to sink and water conditions change, some parts of the foundations became exposed to oxygen and saltwater. This accelerates biological deterioration and chemical erosion, threatening the stability of historical buildings. Second is the impact on public health. During flooding events, the water entering the city is often contaminated with sewage, oil, and urban runoff. Prolonged exposure to polluted floodwater can increase health risks, especially for vulnerable groups such as children and the elderly. Third is cultural and historical damage. Saltwater penetrates into walls of historical structures such as Saint Mark Basilica. When the water evaporates, salt crystal remains inside the mansori and gradually damage the mosaic and the decorative materials. Over time, priceless historical artwork can be permanently lost. As a future engineer, our responsibility is not only to protect infrastructure but also to preserve public safety, cultural heritage, and environmental sustainability for future generations.
Now, I will explain the geotechnical condition of Venice, which is often called the timber pile paradox. Uh, Venice is supported by millions of timber piles driven deep into soft mud layers until they reach a stronger clay layer called Carento. Normally, timber can decay over time. However, these timber piles survive for centuries because they remain fully submerged underwater where oxygen levels are very low. So the engineering problem begins when the city experiences subsidence and changing water level. As the ground sinks, parts of timber foundation and masonry become exposed to oxygen and saltwater. This creates a new environment that accelerates biological decay and chemical erosion. This situation is unusual because the foundation were originally designed to stay permanently underwater, not partially exposed. As a result, the long-term stability of buildings and historical structures become increasingly vulnerable. This is why continuous monitoring and proper geotechnical management are critical for preserving Venice in the future. Next is modern monitoring INSA or interferometry SAR. So research today, known as INSA, together with PSI technology, which stands for persistent scatter interferometry, is based on satellite or radar system that can detect very small ground movement with a very high precision. By using this monitor, the accuracy can reach around zero point 0.3 millimeters per year. that allow engineers and scientists to observe even a tiny displacement on the ground surface. So, for the data collected, the historical center of Venice has remained relatively stable since groundwater pumping was reduced in the 1970s. The displacement rate there is close to 0 millimeter per year. However, the near the lagoon edges are still sinking, but approximately 3 to 5 millimeters per year. In newly developed urban areas, the subsidence rate can increase up to 10 millimeter per year due to additional weight of buildings and infrastructure constructed of young sediment layers. The monitoring system is very important because it can help engineer predict future risks that can engineer protect habitat structures, plan sustainable urban development.
Okay, next we will discuss the sustainable engineering solution implemented in Venice, which known as the MOSE project. MOSE, which is MOSE, stands for Modulo Sperimentale Electromeccanico, and it was developed as a structural defense system to protect Venice from severe tidal flooding. The system consists of 78 mobile flood barriers installed at the three main inlets of the Venice lagoons, which are Lido, Malamocco, and Chioggia. In terms of design mechanism, the barriers are hollow metal gates normally filled with water, allowing them to remain hidden underwater during normal conditions. However, when high tide exceeds approximately 110 centimeters, compressed air is pumped into the gates to remove the water and raise the barrier above the surface. This temporarily blocks seawater from entering the lagoon and flooding Venice. From sustainability perspective, the MOSE project provides several important benefits. First, in terms of environmental sustainability, unlike permanent dams, the MOSE barriers remain inactive during normal tides. This allows natural tidal flushing to continue, helping maintain oxygen levels, water circulations, and biodiversity within the lagoon ecosystem. Second, from a socio-economic perspective, the system helps protect Venice's historic buildings, tourism industry, and cultural heritage while still allowing port and shipping activities to continue operating. Overall, the MOSE project demonstrates how civil engineering solutions can integrate structural protections, environmental considerations, and sustainability urban resilience to address the long-term impacts of ground subsidence and sea level rise in Venice. Okay, next we will look at the role and our professional duties. When working on a site like Venice, it is not just about the technical side. We must follow a clear legal framework. A key part of this is the Special Law for Venice from 1973, which made protecting the city a national interest. This law requires us to find a balance between industrial growth and environmental safety. In terms of engineering rules, there is a total ban on taking groundwater from artisanal well to stop the city from sinking. We also cannot make any change to the lagoon without a mandatory environmental impact assessment, which is EIA. This ensures we understand the effect of our work before we begin. Finally, we use soft engineering by restoring salt marsh or barrens. These marshes act as natural wave breaks to protect the cities. By following these legal and ethical rules, we make sure our work is safe for the future.
So my name is Amir Razik. So I want to talk about a mitigation strategy metrics for the Venice Lagoon. So this is based on the professional responsibility and legal mandates. So firstly, regulatory mitigation, which is the aquifer management. So it's achieve the groundwater extraction. So cause a rapid land subsidence in the Venice. So Italian government was banned artisan well pumping under the special law for the Venice 1973. So industries shifted to the surface water source from the site and the Brenta rivers. So help stabilize the groundwater levels and reduce human-induced sinking of Venice. Second, structural mitigation, which is the MOS project, implemented to reduce the frequent flooding aqua alta in Venice. So it consists of 78 mobile floodgates installed at the lagoon inlet, such as at Lido, Malamocco, and Chiogila. Gates remain on the seabed during the normal conditions to preserve the tidal flow. When the tides exceed the 110 centimeter, it compressed air raises the gates to block incoming seawater, so it can balance the environmental sustainability with the community flood protection. Thirdly, for the mitigation strategy, nature-based soft engineering salt marsh restoration. Basically, restored salt marsh marine help absorb the tidal energy and reduce the erosion. So dredge the sediments are used to rebuild and strengthen the marsh areas. Marsh act as a natural wave barrier to protect the Venice lagoon. So artificial sediment replacement helps the marshes keep up with the rising water levels and subsidence. And lastly, the technical monitoring, SAR interferometry. So engineers use the INSAT technology to monitor land movement in Venice. So it can track the buildings and the monument with the high precision across the lagoon. It also can detect the localized settlement of up to 10 millimeter per year in urban areas. And it can help engineers strengthen the foundation and improve the piling strategies before the structural damage occur.
Last but not least, the part of this presentation is the conclusions. So there are three scope of the conclusion that we have been made. First is safety scope by protecting people and historic buildings from floods. Second scope is by environment, ensuring the lagoon ecosystem stays healthy and clean. Last is law scope by following the 1973 special law that bans harmful groundwater pumping. So that's all from us. Thank you very much.